you can easily get the Young's modulus, right? Once you know any of the stress and the strain on that linear stage, then you can calculate the Young's modulus, right? That's a straightforward one. And then we talk about the elastic deformation stage. As I mentioned, it's more complex, right? So even define the yield stress is arbitrary, actually. So in this class, we use upon the 2% offset yield strength. And we also actually define, say, for example, percentage elongation. And we can also use the percentage reduction in area as ways to define the ductility, right? So another way, actually, to define or to characterize those plastic deformation stage, that can also give us a very useful, property of the metals or any other materials, is we can also do the hardness test. Okay, we can. You guys might know about that, right? The hardness test different material have different hardness. Like which one is the hardest material in the world? Diamond, right? So, okay. Using the hardness testing, what we can do, we also get the characteristic of the permanent or the plastic deformation stage, okay? So indeed, the hardness is what? Is a measure of the resistance of the material to this kind of a plastic deformation, okay? So to measure that one is easy. There's quite a lot of different, hardness tester. One show you here is, we call that a Rockwell hardness tester. So you put the sample, actually that one has a, the sample stage here, you have a indenter. That one usually made out of a diamond or some other very hard material, silicon nitride or those kind of hard materials. Okay, and that has a well-defined dimension there. You put your sample on the stage, and then apply the force, and then you will read your hardness there digitally. Okay, so the same to do this. The step is very easy. You first press the indenter into your material, and the indenter material need to be harder, right? Otherwise it will do the reverse process. Your material will indent into the indenter tape. So you first press the indenter into the metal or other material. Right? This process can also be used for determining like the hardness for ceramics, plastic, and also could even do the plastic surface. And then you will apply the load. When the load is enough, the tip will be pressed into the material. Okay? And in this stage, what we want to do, we want to apply the load. That load is high enough. We don't want the material go into the plastic stage. Otherwise, when you just release the tip, what will happen? It will spring back. Okay, you won't see anything on the surface of the material. Okay, you want to apply a load that is high enough. It will go beyond this elastic range. It will go to any of this plastic range. Okay, so but that means you need to apply in a high enough load, and then after the load is made, or after the indenter makes some permanent or the plastic deformation into the sample surface, you raise up the sample, the tip, and then you will know there's an indentation, there's a reverse indent left by your indenter on the surface of the material, right? And then by measuring this, usually you can use optical way, using an optical state microscope. You can see the dimension of that. Well, sometimes people use a profiler to do that. And then you can measure the depth or the width of the indentation. And then by considering the different shape of the indenter, the widely used one, it just uses stainless steel or tungsten carbide, using a spherical shape, okay, using sphere as an indenter. And if we know, see for example, the dimension of that one, also if we know how wide of the indentation you made on the sample surface, then by using some simple formula, these are related to the kind of like a dimensional transition, you can get the different hardness. That actually, see for example, when we use this formula, using this type of indenter, the hardness we get will be the BHN or the Brinell hardness. So by that means, when you use the different indenter, you could get different values, slightly different values, okay? Because that's the final hardness, it depends on, significantly depends on the shape of the indenter you use, as well as the dimension of these indenter tips, and also depend on the formula you use. Okay, but actually, once again, the hardness testing gives you a relative comparison. Okay, so if you use the same method to test the different materials, say for example, the low carbon steel and the hard carbon steel, you should get different hardness. Okay, that is some kind of an indication, that can correlate to the strength of the material. Okay, that gives you some characterization. Yes.
What if the indenter deforms?
Usually, no. Usually, the most commonly used one we can use, say for example, for the metals, you widely use like a diamond tips. No way for them to deform because they're harder. They should be harder than that. Say for example, when you do the plastic or some ceramics, you can use a tungsten carbide, which is still harder, significantly harder than the material you are testing. So that one is very important. Okay. So nano indenter, UF, we do have quite a few nano indenter here. Okay. So, but it's the most widely used one. This one, and also the diamond pyramid one is also quite often used. Okay. So anyhow, this kind of like up to here, I want to cover in the first exam. Okay. So tonight I will assign a few problems. Okay, in chapter 6 up to here, up to this section. So the first exam will cover all the material up to here. Okay? So now I have about 5 minutes. I want to quickly introduce another concept. Okay, it's still related to the plastic deformation because as I mentioned, the elastic deformation stage is very easy to understand. Okay? Elongate, release, going back. Okay, no more than that. But the plastic stage is very complex. Okay, that depends on a lot of the crystal structure, especially when we talk about metals. Okay, so say for example, if you have a rod, this one actually is a thin rod. If you apply a tensile stress, okay, when the tensile stress is beyond those linear stage, when it goes to the plastic deformation, actually the process is really complex, as I mentioned. But once for the thin rod, you will see very clearly, once the stress is high enough, you see this kind of a sleeping band. So that means it's more like a surface cutoff. But it's not true, but you see this kind of a sleeping. Okay, it's more like generating like a layered structure. Okay, that's very common. Next time, for many of the metals, you will be able to see this kind of, this is from the top view, this is the cross-sectional view. First, the dimension getting reduced because it's undergo the plastic deformation. It's becomes elongated, so the diameter getting smaller. But during this diameter reduction process, you see these kind of sleeping bands. Okay, sleeping band is because of what? Once again, it's because of the structure. Okay, the crystal structure determines their properties in the deformation process. Okay, so what happens here actually, conceptually you can think about that. When you apply a force, dimension getting reduced, right? Because it becomes elongated. Okay, so the diameter getting smaller. So you can think about it, it's more like a stressing process occurs along the diameter direction. Okay, then indeed, don't forget, you have a crystal, right? These are metal. When we talk about metal, we talk about crystals. The different crystal plates could share a line with each other, generating this kind of sleep bands. We call that sleep bands. Okay, sleep bands. If you think about that one, if you take a look, this one is kind of like a lightly deformed aluminum. You will see these kind of dark lines. Those are caused by the sleep bands. Okay, very easy to see this. For the real sample, you can see those kind of like parallel lines also. So, but if we really think about if it's really the share of the different planes between the planes, that might be too much energy penalty there. Okay, so indeed, in the real process, it's not like one plane actually one crystal plane sliding on the bottom one. It's not that. Otherwise, too much energy. There's not enough energy during the stress process. Indeed, what finally we found is not that process. The sleeping band formation is because of the consecutive or the constructive movement of the defects. Okay, those defects are moving from one plane to the other. In this case, you don't need to share align all the atoms in the neighboring planes. Otherwise, too much energy need, to cause this kind of a sleeping. But this case, only those defects, when you push the sample, only those defects are moving across, or in this case, it's edge dislocation. Remember, chapter 4, when we talk about that one? These are the edge dislocation. The edge dislocation will move across the sample. That will lead to the formation of this sleep band. And the energy required for moving these atomic defects is much, much less. Okay, so by that means we do not talk about the sharing of all the atoms in the whole plane. We only talk about moving of some line defects across the crystal surface. So only very limited number of atoms are consecutively moving here. So therefore, the energy requirement is much, much less. Okay, this is the last slide before I stop here. Okay, so when we talk about the sleeping crystals, one thing important is if we think about the single crystal, or that means when we have a close packed arrays, like this one, say for example, if you have a hexagonal ordered atoms on the bottom and then another close packed one on top, if you take a look of these sleep planes, those planes are really slanted. So that means if you want to move the top plane against the bottom, the resistance between the movement is small. But if you have non-close packed arrays, or that means in the multi-crystalline stage, the force you need to apply to move the top the atoms will be higher because the resistance from the bottom spheres will become larger. Okay, so that means when we talk about the sleeping band formation, single crystal or the close packed planes, energy requirement is less than the polycrystalline. Okay, so I will show you why this discussion is important in that after the first example.